So sections 10.3 and 10.4. 10.3 is mostly just applications. So it's kind of, but they're gross, right? Like it's like, it's the normal stuff, but it's all these letters and things that are just kind of hard to deal with. But let's look at an example. And I definitely have a couple. And one of them is one of your homework problems. I don't particularly care. Where'd you go? Example. So this is 10.3 number 2. I don't feel the need to write out the entire words of all of it because there's a lot of words. So let's read the words and then I will write down the pertinent information, which is also what I would like if I was doing this as a student. I definitely wouldn't write out all the words. I would write down the important equations and maybe some other things. Let's see what we've got here. So hemodialysis is a process by which a machine is used to filter urea and other waste products from a patient's blood if the kidneys fail. The amount of urea within a patient during dialysis is sometimes modeled by supposing there are 2 compartments within the patient: the blood, which is directly filtered by the dialysis machine, and another compartment that cannot be directly filtered by, but that is connected to the blood. A system of 2 differential equations describing this is the following. So we have dc dt equal to negative k over v times c plus ap minus bc. And then we also have dp dt equal to negative AP plus BC. And they tell us C and P are, so C is the concentration, of urea in the blood, and P is the concentration of urea in the inaccessible pool. Concentration of urea in the pool. And then we're supposed to do a few other things as well. So when they say all constants are positive, so it's worth noting that the constants, which there are many, right? There's K, V, A, and B. Those are all positive. Additionally, we're going to suppose that K over V is equal to 1/2. Oh, sorry, not 1/2, 1, apologies. A and B are both equal to 1/2. And the initial urea concentration is that C of 0 is equal to C naught, and P of 0 is equal to C naught as well. Good times. I feel like that must be a mistake. I feel like it's supposed to be P naught. Like, I'm pretty sure that should be, it wouldn't make sense for P of 0 to be C naught. It just, I'm going to change that to P naught. Pretty sure that's sometimes books have typos. So first, we want to classify the equilibrium. Welcome, thanks. What's that? Oh, thanks, yeah. We're just working on problem number 2 from section 10.3. Let me see one thing here. That's fine, okay. Again, so has he talked about compartment models at all? Or had any problems with compartment models? The reason I ask is because you could draw a compartment model here. So you could say, if just as a point of interest, if this was a compartment that had the concentration of concentration of urea in the blood, and this was the compartment over here with the concentration of urea in the pool, then you could say, well, looking at these equations, we can see that the concentration in the blood, you're losing B times it to the concentration in the pool, which makes sense because the concentration in the pool is gaining B times it. And similarly, the concentration in the pool, you are losing A times it, or I should say that's B times C, and this is A times P. And then additionally, dc dt, you are losing this k over v times c. So that would be the compartment diagram for this. Really, the compartment diagram is just arrows going in means you're adding those things in, arrows going out means you're taking those things, subtracting those things out. So this plus AP, I have an AP going in to C, and this minus BC and this minus K over VC, you have arrows going out. And then for dP dt, the minus AP is an arrow going out, the plus BC is an arrow going in. Again, not super important if you don't have to worry about that, but it is something people sometimes talk about, so it felt like it was a good time to mention it. So we want to classify the equilibrium, which is your usual kind of question, right? So first we have to find it. So let's see. Our equation is going to look like dc dt equals, so let's plug in some values. So it's going to be negative c plus AP, so 1/2 p minus 1/2 c, which I should simplify as dc dt equals negative c minus 1/2 c is minus 3/2 c plus 1/2 p. And dp dt is, I really should be consistent with the order I write the variables in. So since I've just kind of thinking of c is the first thing and p is the second thing, I'm going to write the second equation that way as well, where I'm going to have a 1/2 c minus a 1/2 p. Great. I can now write my matrix. So my matrix is going to be negative 3/2, 1/2, 1/2, negative 1/2. So it's not, this one's actually not so terrible once you put the numbers in, right? It feels not unreasonable, I suppose. So then if I want to find the eigenvalues, there's literally so many ways we can find the eigenvalues. But so I'm going to do it the way I've seen him do it in class most of the time, which is where he finds the determinant, he finds the trace, and then he actually writes down the quadratic equation from that. So we can see that the trace of this matrix is negative 3/2 plus negative 1/2, which is negative 2. And then the determinant of this matrix is negative 3/2 times negative 1/2, which is positive 3/4, minus 1/2 times 1/2, which is 1/4. And then you would write the quadratic equation. So the quadratic equation is going to be lambda squared plus 2 lambda plus 1/2. Because it's lambda squared minus the trace times lambda plus the determinant equals 0. And so then our solution would be lambda equals to negative 2 plus or minus the square root of negative 2 squared, or sorry, yeah, no, sorry, 2 squared, apologies, minus 4 times the determinant, which is 1/2 all over 2. So we end up with negative 2 plus or minus the square root of 4 minus 2 is 2. And so here's what I would point out. We know they're both real because they're not complex, right? We don't have a square root of a negative. And we know at least one of them is negative because you have negative 2 minus root 2. And then the other one, so this one I feel like is easy enough to be like, well, I know negative 2 plus root 2 is also a negative number. But if you didn't, another you can justify it saying, well, the other one is either negative or positive. If it were positive, we'd have to have a saddle. But we know we don't have a saddle because the determinant was positive. Then we get a saddle, so the determinant's negative. So you can then justify, oh, the other one has to be negative 2. So both eigenvalues are negative, which means we have a stable node. All right, let's look at the second part, which is solve the initial value problem. So they actually want us to write the solution. This one's going to get a little messy. It's always a little messy when your eigenvalues are not nice integer numbers. So let's go on and on and on. So are the pertinent details. Our matrix, once again, is negative 3/2, 1/2, 1/2, negative 1/2. And our eigenvalues are -2 plus or minus the square root of 2 all over 2. Or I would probably write them as -2 over 2 plus or minus root 2 over 2, like that. Okay. So then we need to find the eigenvectors. And in this situation where your eigenvalues are not nice, I would do it the a minus lambda I times your eigenvector equals 0 kind of way. So we're going to solve a minus lambda I times your vector equal to 0. Okay, so we're going to have, so you have to be careful. -3 have to minus that. And let's do the plus one first. So we're doing lambda 1 equal to -1 plus root 2 over 2. And then we have a 1/2, and then we have a 1/2, and then we have a -1/2 minus -1 plus root 2 over 2. And let's simplify that a little bit because it's, again, a little bit gnarly. -3 has plus 1 is -1/2, and then minus root 2 over 2. We have a 1/2, we have a 1/2. -1/2 plus 1 is +1/2 minus root 2 over 2. Times your xy should equal 0, 0. Matter of personal preference, I like to let x be 1 and y be some multiple of x, essentially. So if I was picking which one to do, I would pick the one where the coefficient of x is less nice. So I'm going to pick the first row to write my equation. So I'm going to say I'm going to have -1/2 minus root 2 over 2x equal to, plus 1/2 y equal to 0. Just doing that row with that column. I'm going to bring this over to the other side. Okay, really, let's be not silly about this. Let's multiply everything by 2 before I do anything else, right? That seems like a thing we could do that would make our lives better. So we're going to multiply by 2 and get -1 minus root 2 times x plus y equal to 0. And then bringing this over to the other side, y equal to +1 plus root 2 times x. So my eigenvector here is going to be x equal to 1, y equal to 1 plus root 2. So here's a nice thing that I don't think anyone has said in your class maybe, but it's certainly true. Just like with complex eigenvalues and eigenvectors, how if you get a complex eigenvalue, the complex conjugate is also an eigenvalue. And for the eigenvectors, once you find one eigenvector, you just take the complex conjugate of it and change all the imaginary parts to their opposite signs. That is also true when your eigenvalues and eigenvectors are irrational, meaning the other eigenvalue here is the conjugate. Lambda 2 is -1 minus root 2 over 2. And it is true, and we can show it if you guys want to, but you can also just believe me that the second eigenvector is this same eigenvector, but we're going to change the sign of the irrational part. So it's going to be 1 minus root 2. I feel like it's worth showing it though, but it is true. Let's show it though. So, well, in fact, so we're going to show it in kind of the laziest way possible by adding a minus sign to everything. So all I'm doing for my eigenvalue is changing this plus sign to a minus sign. So that would have been a minus sign, and that would have been a minus sign, which means then this would have been plus root 2 over 2, and that would have been plus root 2 over 2. And then in this equation, I would have had a plus root 2 over 2. And then that would have been a plus root 2. And then that would have been a minus root 2. And so if x is 1, y is going to be 1 minus root 2. Oh yeah, it works out. But it's much better than doing all the work. But it is really true. So if you have irrational eigenvectors and eigenvalues, they really do come in these kind of pairs where you just change the sign of the irrational part, which is great. But wait, there's more. We're not done yet, right? We have to find the particular solution. So then we say, all right, we know the general solution is going to be your usual hot mess of x as a function of t is c1 e to the lambda 1t v1 plus c2 e to the lambda 2t v2, which is equal to c1 e to the lambda 1. Okay, all right. So lambda 1 is -1 plus root 2 over 2 t times my v1, which is 1 plus root 2 plus c2 e to the -1 minus root 2 over 2 t times your v2, which is 1 and then 1 minus root 2. Stay on the page. And then we find C1 and C2. So then we have to go back and remember what our initial conditions were. I know I wrote them down somewhere. Oh yeah, this is where it's really lovely. Our initial conditions were C sub 0. C of 0 is equal to C sub 0, and P of 0 is equal to P sub 0. How helpful. So we're going to plug in t equal to 0, and this for the first coordinate, this for the second coordinate. So we're going to get, this is probably where it gets ugly. So let's see, plugging in t equal to 0, we're going to have x of 0 should equal c naught p naught, and then it's going to equal c1 e to the 0 times 1 plus root 2 plus c2 e to the 0 1 minus root 2. Okay, then sorry, just laugh because the problem is I feel like it's so much like just goes on and on and on. So then we're going to do the thing where, yeah, how do I want to do this? Well, I'm just going to write my equation. So I have c1 plus c2 equal to c naught, and c1 times 1 plus root 2 plus c2 times 1 minus root 2 equal to p naught. Just to solve for c1 and c2. Okay, I guess I would probably, what do I really want to do here? I guess I would solve, I would, yeah. I don't love that, but I guess I would do it. I would isolate one of these two here. So C1 equals C naught minus C2, and then plug that in for C1 over here, and then solve for C2. It's not going to be pretty. No, that seems, yeah. Okay, maybe it will be. Actually, it looks like it's not as ugly as I thought it was going to be. Let's find out. Oh, no, I see. Okay. So I will admit, I said we should change it to P naught because I was reading someone else's notes and they're like, we should change it to P naught. But it feels like maybe we do actually want it to be C naught so that things are not terrible. Yeah, that's probably really the case. I see. So really, this actually is what the book said. The book was not wrong. I was just making an assumption based on it seemed reasonable. Okay, so then we're going to plug that in there. We're going to get C naught equal to, oh boy, C naught minus C2 times 1 plus root 2 plus C2 times 1 minus root 2. Multiply it out. So we're going to get C naught plus root 2 times C naught minus C2 minus root 2 times C2 plus C2 minus root 2 times C2. Hopefully some stuff cancels. I think we do. Let's see. Minus root 2. No, that doesn't cancel. Negative C2, positive C2 cancels. A C naught and a C naught cancel. So I think we're left with, and we're trying to solve for C2. So we're going to have a root 2 C naught equal to a positive 2 root 2 C2. So solving for C2, we get C2 equal to root 2 C naught divided by 2 root 2, or 1/2 C naught. Wow. Okay. And then we can plug that back in up here and say, oh, well, if that's C2, then C1 is going to be C naught minus 1/2 C naught, which is also 1/2 C naught. So finally, we get that x as a function of t, or whatever you want to call this vector, is 1/2 e to the lambda 1 t times 1 plus root 2 plus also 1/2 e to the lambda 2t times your v2. That's kind of a lot. It's definitely not a good test question, but it definitely is. I mean, it's a fine homework question. Should we look at another problem from section 10.3 or should we do some stuff from 10.4? Okay, that's what I was thinking too. So the 10.3 problems are just, I mean, you really kind of just have to like fight through it, right? It's gross. Let's look at section 10.4. And where'd you go? I have a good example already. Yeah, let's look at this example. Oh, this is a problem from 10.4. Let's see if it's cool. So this is problem 10.4 number 7. And I will admit, this is something that I have never really paid a lot of attention to, specifically the finding the linearization of the system of differential equations at the equilibrium, but we can totally do it. So all we're going to be doing is finding the equation of the tangent plane. It's just called linearization. And really, it's kind of a use the formula kind of situation. But let's start with our differential equations. We have dx1 dt equal to -5x1 plus x1 x2, and dx2 dt equal to x2 minus 5x1 x2. And if we weren't being super careful, we might make the mistake of saying that these were linear. They're not linear, but we don't see any powers of x1 or x2 that are other than 1, so it feels like it could be kind of linear, but it's not because you have the x1 times x2. So definitely not linear. I'm just pointing this out because I could totally see someone asking a question like, is this system a system of linear differential equations or nonlinear differential equations? And this would definitely be nonlinear. And I think that would be I think that'd be a fair test question that's easy to get right, and it's also easy to get wrong if we're not paying attention. So we want to find the equilibria by setting those equal to 0. And setting them equal to 0, I'm going to do some factoring. I'm going to factor out an x1 here. So x1 times -5 plus x2. And here I'm going to factor out an x2. I'm going to be left with a 1 minus 5x1, both equal to 0. Okay, so in this first equation, what's one way this first equation could be 0? Well, x1 could equal 0. Or what else? What could x2 be? Yeah. Now I really have to stress 0, 5 is not an equilibrium. X is 0 and x1 is 0, x2, sorry, x1 0 and x2 5, not an equilibrium. It makes this equation 0, but those values don't make this equation 0. Right? If you plugged in 0 for x1 and 5 for x2, you get 5 times 1 minus 0, which is 5. So the point I'm making is both equations have to be 0 at the same time. So this other one, we're going to get x2 equal to 0 or x1 equal to positive 1/5. Okay. So let's see what happens when we pair those up. Well, really, we have to have one of these and one of these. So we can have x1 is 0 and you can't have that. x1 is 0. So that one. So 0, 0 is one of our equilibria. And then you could also have x1 being 1/5, but then if x1 is 1/5, we have to have x2 being 5. So in this case, the only way we can get equilibria are the following two. They're going to be 0, 0 and 1/5, 5. And our notation for that is this whole x1 hat, comma x2 hat. Those are equilibria. And then this equation that I honestly have a hard time remembering. Yeah. So here's what our linearization looks like. So the linearization, which some people write, I suppose, as L, yeah, L of x1, x2, is the following very, very general formula. It's, yeah, and I think he likes to call this one F1 and this one F2. So it's the vector F1 evaluated at x1 hat, x2 hat, F2 evaluated at x1 hat, x2 hat, plus, he doesn't write, I'm sorry, I'm doing it in a slightly different way. I feel like it's maybe the less good way of doing it. He's doing it slightly differently in class, which is fine. Yeah, sorry, let me actually do this slightly differently. So for F1, the linearization is going to be, sorry, I always want to use X and Y. It's going to be F1 evaluated at the equilibrium plus the partial of F1 in the x1 direction evaluated at the equilibrium times x1 minus x1 hat plus the same thing in the x2 direction. So the partial derivative of F1 in the x2 direction at x1, x2 hat times x2 minus x2 hat. Nice. It's messy. I know, I'm saying that a lot. It's because it's true. A lot of these things are a little messy. So this is going to end up being, so here's the thing, this F1 of x1 hat, x2 hat, when you plug in the equilibrium point to the function, to the derivative, what do you get when you plug in the equilibrium? Right, you get 0. This should always be 0 at an equilibrium. So what we're going to get here is that the linearization of the first equation at x1 comma x, or let's actually pick a point. We're going to do it at 0, 0. It's going to be 0 plus the partial derivative of this with respect to x1. So -5 plus x2, but we're plugging in 0 for x2. I should show my work a little bit. Yeah. Times x1 minus 0. Brain, yeah. Plus the partial derivative of f1 with respect to x2, which is x1. And then we're plugging in x1 hat times x2 minus x2 hat. Woof. And then we actually need to plug in the x2 hat and the x1 hat values, which are these things right here. So we're going to get -5 times x1 plus x1 hat, which is 0. Kind of boring, but fine. Yeah, that's really. So I double check my work here. Yeah, that looks fine. And then we would do the same thing for F2. So then we're going to do, now let's be a little more, what's what I want to look at? Let's actually just start with, we know we're doing 0, 0. So doing 0, 0, it's going to be 0 plus, now it's the partial derivative of F2 with respect to x1. So the partial derivative of F2 with respect to x1 is going to be, that with respect to x1 is going to be -5 x1. We're going to plug in x1 equal to 0, and then we're going to multiply by x1 minus 0 plus, man, the work here is gnarly. Partial with respect to x2, that's going to be 1 minus 5x1. We're going to plug in x1 equal to 0 again, and we're going to have times x2 minus 0, which ends up equaling 0 plus 1 minus 0 times x2. Hooray. So here's what we're saying. We're saying that at the equilibrium 0, 0, the system of differential equations essentially looks like dx1 dt equals -5x1 and dx2 dt equals x2. That's what the linearization is telling us there. It's kind of super gnarly though. Interesting. Oh yeah, that's with that one. So let me check one thing here. Oh, I see. Okay. I'm looking at, yeah. Okay. Let's do the other one because there's also another equilibrium. So let's look at equilibrium 1/5, 5. So x1 hat, x2 hat equals 1/5, 5. So again, for F, by the way, this is a really good time to really encourage you to use F and G instead of F1 and F2. F and G is a little bit less notationally terrible than F1 and F2. I know he uses F1 and F2 in class. It doesn't mean you have to. I feel like I should though because that's what he's doing. So now we're going to do the same equation, right? The same as before, except now instead of plugging in 0, 0, we're plugging in 1/5, 5. So we're going to get that our linearization for the first function, so f1 of x1, x2 is approximately this first linearization, x1, x2. And it's going to end up being, well, these, so this is our x1 hat. I just wrote that over there. I'm writing it again. So it's going to be the partial derivative with respect to x in the, oh my gosh, partial derivative of the first one with respect to x1, which we did already before. So it's going to be that same first partial derivative. It's going to be -5 plus x2 times x1 minus the x1 hat value. And then we're going to have plus the partial derivative with respect to x2, which was x1. Yeah. Careful. Sorry, I'm getting a little, no, let's see. With respect to x2. Yeah, okay, yeah, x1. Right, it's a lot to keep track of. x1 times x2 minus x2 hat. And then we're plugging in 1/5 and 5. So we're getting, I guess this should actually be a hat here, and this should be a hat here, because we're evaluating the partials at the point. This notation is not my favorite. Okay, so then we're going to get -5 plus 5. Doesn't really matter what the rest of this is. And then we're going to get plus 1/5 times x2 minus 5, which ends up being 1/5 x2 minus 1. Wow. Okay, let's do the other one. So f2 of x1 comma x2, it's approximately L2 of x1 comma x2, which is again, so I think I'm going to write the formula again just to remind everybody what it is. Right? We're taking the partial of f2 with respect to x1 times x1 minus x1 hat plus the partial of f2 with respect to x2 times x2 minus x2 hat. I feel like there's something else I want to mention. No, I guess not. So there's our f2 up there. The partial of f2 with respect to x1 is -5x2. So it's -5x2. And really, I'm going to be plugging in the equilibrium there. So it's really -5x2 evaluated at the equilibrium. So it's -5x2 hat times x1 minus x1 hat plus, now this partial with respect to x2 is going to be 1 minus 5x1, but I'm going to plug in the equilibrium. So it's really x1, excuse me, hat times x2 minus x2 hat. And then finally, we plug in our values, 1/5 for x1 hat, 5 for x2 hat. and we get negative 25 times x1 minus 1/5 plus 1 minus 0, sorry, 1 minus 1, which is 0. It doesn't really matter what this is. So we end up getting that the linearization of f2 is negative 25 x1 plus 5. Interestingly, these are both non-homogeneous, right? You have something extra added on at the end. So yeah, it's kind of a lot. It's not, I just wish the notation was better, right? It's not terrible, except that the notation is kind of terrible. Yeah. Should we do another one? Let's do another one, and let's write it. I'm going to show you how I would prefer to write it slightly nicer. So let's look at which one. Let's look at not 11. Let's look at 9. So here's 10.4, number 9. So here's our situation, and so here's what I would encourage you to do. I'm going to use x and y first of all. These subscripts, when you're trying to take partial derivatives, just make things harder. So instead of writing dx1 dt and dx2 dt, I'm going to say dx dt is going to be x minus 6y squared plus xy. And dy dt is going to be 8x plus 4xy. So first, let's find the equilibrium. Setting them both equal to 0. Yeah, that doesn't look so great. So if I were trying to deal with this, usually you're going to want to try and flow towards the one that's easier or simpler to deal with. To me, it definitely looks like the second one is easier to manage. So if I try and deal with this one, I can definitely factor out a 4x. If I factor out a 4x, I'm left with a 2 plus y. Okay, that's pretty promising, because then I can see that either x needs to be 0 or y needs to be negative 2. And then I can plug either one of those back into this first equation. So in this first equation, if I set x equal to 0, what do I get? Well, I get 0 minus 6y squared plus 0 equal to 0. So y has to equal 0. It's not always 100% of the time going to be true that you're going to get 0, 0 as an equilibrium, but it's often very true. You're going to get 0, 0 as an equilibrium. And then if y equals negative 2 for this equation, well, then I'm going to get x minus 6 times 4 is 24 minus 2 times x equals 0. So it looks like I have x minus 24 equals 0. So it looks like I have x equal to 24. So it looks like my other equilibrium is 24 comma negative 2. Does that seem right? We can check. If you plug it into these equations, if x is 24, I'm going to have 24. That seems not right. I feel like I made a mistake. Let's check. So it's good to check sometimes. So if you do plug in 24 and 2 for y, oh, it's a negative x, right? X minus 2x is a negative x. So you should be getting x equal to negative 24. And now if I plug in negative 24, let's see. Negative 24 and then minus 6 times 4 is another minus 24, so minus 48. And then plus x times y, it's 48. Yeah, that works out. That's 0. So good. Okay. And now we want to find the linearization. So linearization, instead of writing it the other way, here's how I'm going to write it this way. My linearization, I do think he has been writing it not as a matrix, right? Like he's never done it where you've done both linearizations at the same time. He's always written them as 2 different equations. You can write it as a matrix. I think it's kind of easier not to. Let's call this F. Let's call this G instead of F1 and F2. So then the linearization for f is going to be brain, yeah. And we're gonna, let's do it first at 0, 0, even though it's not as interesting. So it's going to be f of 0, 0 plus fx at 0, 0, comma x times x minus 0 plus fy at 0, 0 times y minus 0. F at 0, 0 should be 0. What's our fx here? And I really do actually want you to tell me. If I take the partial derivative of f with respect to x, what do I get? Let's see, if I take the derivative of that with respect to x, I'm going to get 1 plus, that's going to be 0, and then the derivative, that's going to be what? Right. So I'm going to get 1 plus y, and I'm going to evaluate that at 0, 0. Right, because I'm taking the partial derivative at the equilibrium. And then I'm going to multiply that by x. And same deal over here, fy is going to be 0 minus 12y plus x evaluated at 0, 0 times y. And then plugging things in, we end up getting 0 plus 1 times x plus 0 times y. So our linearization of this first differential equation in the linearization at near the equilibrium 0, 0 is just x. Okay. And then we can do the same thing for the second one. That's going to be g at 0, 0 plus the partial of g at 0, 0 times x minus 0 plus the partial of g with respect to y at 0, 0 times y minus 0. So that's going to end up being 0 plus the partial with respect to x is going to be 8 plus 4y evaluated at 0, 0 times x plus the partial with respect to y is going to be 4x evaluated at 0, 0 times y. And this one ends up being 8 times x. Not particularly exciting, but that's okay. Let's look at the other one, because the other one's a little more interesting. But again, so really what I should say about this linearization stuff in section 10.4 is it's kind of just this. Right? I mean, a lot of this is kind of just where you saying, here's my formula, and then just throw everything into it and just make sure you keep track of the stuff. Right? It's a lot of keeping track of what's going on. So we're going to look at these again, but now instead, right? So this is where it's good to have your work in front of you, because I already know what all the things are. So now if I want to find the linearization of f, but now at the point -24, -2, well, it's still going to be f of -24, comma -2, plus I already know what my partial derivative is, right? It's still 1 plus y, but now it's 1 plus y evaluated at this point, -24, comma -2, times x minus this x coordinate, plus my partial derivative with respect to y, which is still the same thing. It's still -12y plus x, but now it's evaluated at this point, and it's multiplied by y minus this y coordinate. So if you have to do this linearization thing for more than one point, it's good to keep your work for the first point in front of you, because the sum of the work carries over. And so simplifying this, we're going to get 0 plus, if I plug in y here, I'm going to get a -1 times x plus 24. Plus, if I plug in x and y here, I'm going to get a, not surprisingly, a +24 minus 24, which is going to be 0 times y plus 2. So I'm getting -x minus 24. That's my linearization near that point. And then we'll do the same thing for the second equation. We're going to get, it's going to be 0 again, right? I didn't even check plugging it in. I knew it was going to be 0 because it's an equilibrium. So you're going to get this g of -24 comma -2, which we know is going to be 0. Plus, now these partials, so that partial is 8 plus 4y, evaluated at this point, -24 comma -2, times x minus -24, plus that partial 4x evaluated at -24 comma -2. No, that's fine. Yeah. Times y minus -2. So we're going to end up getting, let's see, 8 minus 8 is 0 times x plus 24 plus 4 times -24 is -48 times 2 is -96 times y plus 2. So we get -96y minus 192. So that would be the linearization of this particular system of differential equations near that point. So one thing you could say, you really wanted to, about this first one is, no, I don't really want, bless you, wow. Yeah, I don't really want to say anything. What I do want to say though is, we can also use these partial derivatives to help us classify the equilibrium. Not that we're being asked to do this, but you could totally, for this equation, say, okay, for, again, we have the same dx dt equal to x minus 6y squared plus xy and dy dt equal to 8x plus 4xy. We could also try to classify the equilibria. So the way we classify the equilibria, well, there's a couple ways. I don't think he's talked about the graphical method, right? I hope. I mean, it's not terrible. The graphical method is kind of neat. The reason I asked is because I saw someone asked me earlier today in office hours about it because it was on one of his practice tests from a few quarters ago. So I would like to imagine if he hasn't talked about it in class, it's not something you're responsible for. I also haven't seen any homework problems on it anywhere. So I would imagine it's not fair game, but just pay attention to class today, I guess, and see if he says anything about it. I don't think he will. I'll definitely watch the video later and see if he does. But what I would say here is we can classify these equilibria 0, 0, and -24, -2 using the Jacobian. So the Jacobian is, that's why I like to call this F and this G. Jacobian's just fx, fy, gx, gy. I really have to say, look how much nicer it is to write that than f1, x1, f2, x1, f, right? It's a little, there's also good reasons for using x1, x2, but this is just nicer sometimes. So let's see, that's going to be fx, which we know is 1 plus y, fy, which is -12y plus x, gx, which is 8 plus 4y, and gy, which is 4x. And so if we look at 0, 0, our Jacobian there is going to be 1, 0, 8, 0. Oh. This is kind of a weird situation. Where are eigenvalues here?
1.
And yeah, I think even 0 is an eigenvalue. So I think he talked about it in class a while ago. Basically, when 0 is an eigenvalue, saved by the bell. I'll think about it. Let's look at, so we'll work on that. Let's look at the other one. If I plug in negative 24, comma, negative 2, I end up getting, see, negative 1, negative 24 plus 24 is 0. I get, doesn't really matter what this is going to be down here at all. Actually, I could totally ignore this entry right here because once I have a 0 there, I know only the diagonals matter. And so I'm going to get negative 96 here, and I don't care what's here. It's going to be 0, but I don't really care. So here my eigenvalues are negative 1 and negative 96, which means we would have a stable node because they're both negative and real.